Hello student. In previous video lecture we have seen that the concept of Poisson distribution, probability mass function of Poisson distribution, mean and variance of Poisson distribution. Now in this video lecture I am going to explain the moment generating function of Poisson distribution, cumulative generating function of Poisson distribution. Now first we see the moment generating function of Poisson distribution. Okay, now see the probability mass function of Poisson distribution is if x follows Poisson distribution with parameter m, then its PMF is given by probability mass function. Probability of x equal to small x, which is equal to e raised to minus m raised to x upon x factorial. Here x takes values 0, 1, 2, dash 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 up to infinity. 0 otherwise, and here m is greater than 0. This is the probability mass function of Poisson distribution. Now to obtain the MGF of Poisson distribution, now by definition of MGF we have mx of t is equal to expected value of e raised to t into x. Now by definition of expectation, which is equal to summation of e raised to t into x into probability of x equal to small x, here summation over x. This is the definition of moment generating function. Now here we substitute probability mass function of Poisson distribution. This is the probability mass function of Poisson distribution, now which is equal to summation of e raised to t into x into e raised to minus m raised to x upon x factorial. Here summation over x takes values from 0 to infinity. Now this can be written as, here e raised to minus m is the constant term, take out of summation sign, which is equal to e raised to minus m into summation of e raised to t into x into m raised to x upon x factorial, summation over x running from 0 to infinity. Now this e raised to t into x, this can be written as e raised to t into x, which is equal to e raised to t bracket raised to x. Okay, now which is equal to summation of, first write down e raised to minus m, e raised to minus m into summation of e raised to t bracket raised to x into m raised to x upon x factorial summation or x running from 0 to infinity. Again, this can be written as e raised to minus m into summation of m into e raised to t bracket raised to x upon x factorial summation over x running from 0 to infinity. Now substitute x equal to 0, x equal to 1, x equal to 2, x equal to 3. We have a one series, and then we obtain the sum of this series. Now this is equal to mgf of x, that is mx of t is equal to e raised to minus m into in bracket. Now put here x equal to 0, then we have first term is equal to 1 plus second term is m into e raised to t upon 1 factorial plus next term is m into e raised to t bracket complete bracket square upon 2 factorial plus m into e raised to t bracket raised to 3 upon 3 factorial plus 1. We have this series, and we know that sum of this series is equal to e raised to m into e raised to t. Okay, now which is equal to e raised to minus m into e raised to m into e raised to t. This is the sum of this above series. Now this can be written as e raised to minus m plus m into e raised to t. Okay, then which is equal to, from this can be written as which is equal to m into in bracket e raised to t minus 1. This is the mgf of Poisson distribution with parameter m, moment generating function of Poisson distribution. Okay, now we obtain cumulant generating function of Poisson distribution. Next one is cumulants of Poisson distribution. Cumulant generating function. Cumulant generating function in bracket CGF. Okay, the CGF is denoted by kx of t, that is cumulant generating function of random variable x, which is equal to what? Log of mgf, log of moment generating function. This is the definition of cumulant generating function. Okay, now we know that moment generating function of Poisson distribution is equal to e raised to m into in bracket e raised to t minus 1. Substitute this mgf in the kx of t, which is equal to log base e of e raised to m into in bracket e raised to t minus 1. Okay, and this is equal to m into in bracket e raised to t minus 1. Log of this term is equal to this one, m into in bracket e raised to t minus 1. K x of t is equal to m into in bracket e raised to t minus 1. Now we know that e raised to t is equal to, which is equal to m into in bracket e raised to t. This is equal to 1 plus t plus t square upon 2 factorial plus t cube upon 3 factorial plus so on. This is in the first bracket minus 1, this one minus 1 square bracket complete. Now the plus 1 and minus 1 gets cancelled, then we have only m into in bracket t plus t square upon 2 factorial plus t cube upon 3 factorial plus t raised to 4 upon 4 factorial plus dash dash dash, the square bracket complete. Okay, this is the kx of t, cumulant generating function of Poisson distribution. Then we have to obtain the cumulants of Poisson distribution, the first 4 cumulants of Poisson distribution. Then k1 is equal to first cumulant, which is equal to coefficient of t upon 1 factorial in the expansion of kx of t, in expansion of kx of t. Okay, then we know that the coefficient of t is equal to m only, the coefficient of t which is equal to m, that is k1 is equal to 1. Therefore k1 is equal to m, which is equal to mu1 dash. This is the first cumulant of Poisson distribution. Now the second cumulant of Poisson distribution is equal to k2 is equal to, k2 is the second cumulant of Poisson distribution, k2 equal to coefficient of t square upon 2 factorial in kx of t, in the expansion of kx of t here. Okay, the coefficient of t square upon 2 factorial is equal to again m, that is k2 is equal to m. Okay, then also we can obtain the k3 and k4 similarly. k3 is equal to third cumulant of Poisson distribution, which is equal to coefficient of t cube upon 3 factorial in kx of t, and the coefficient of t cube upon 3 factorial is equal to again m, which is equal to m, means k3 is equal to m. Then Fourth cumulant of Poisson distribution is denoted by K4. Then K4 is equal to coefficient of t raised to 4 upon 4 factorial in the expansion of kx of t, and the coefficient of t raised to 4 upon 4 factorial is equal to again m, that is k4 is equal to m. Then we can now conclude that all the cumulants of Poisson distribution are equal to m, that is k1 is equal to k2 is equal to k3 is equal to k4 is equal to dash 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 is equal to m. All the cumulants of Poisson distribution are same and which is equal to m. Okay, now we obtain central moments using these cumulants. Central moments of Poisson distribution. Central moments. Central moments. Okay, now B1, the first order central moment is equal to 0, and that is always 0. Second one is mu2 is equal to k2 is equal to m. Then mu3 is equal to k3 is equal to m. Next one is mu4 is equal to k4 plus 3 into mu2 square, that is k4 is equal to m plus 3 into m square. This is the first 4 central moments of Poisson distribution. Mu2 equal to m, mu3 equal to m, mu4 is equal to m plus 3 into m square. Okay, thank you.